Yeah, so today I'll be talking to you about the atomic cluster expansion and hyperactive learning, and how we're going to use both of these frameworks combined to model the physical phenomena in polymers and alloys with quantum mechanical accuracy using these ACE interatomic potentials. And I wanted to start off today with this image, sort of illustrating the rebranding of linear regression over the last 10 years, whereas in 2009 it was called statistics, and in 2019 it was machine learning. And we were discussing this with Gab, and he was saying, well, actually, that's not quite right, because Gauss and Legendre did it in 1800, and IBM, they were doing this on punch cards in 1920. But again, today, this remains very relevant, and all my talk today is, again, on linear regression. I'm going to rewrite it slightly differently, and sort of the two main things to discuss is that you have your observations collected in Y, which are the number of observations you're going to fit, and for us, it's going to be energies, forces, and stresses you obtain through some quantum mechanical method. And your C is the number of features or basis function you're going to use to do your fit, and basically all the idea is putting all the science or try to create a design matrix psi which you can solve essentially, and the aim is what kind of size for N and M do we need to do new science. And with new science I mean determine the melting temperature of an alloy, quantum mechanical accuracy, or determine the density of a polymer. This actually requires us to answer two questions. First of all, how much data do you really need to get sort of a melting temperature, and also how many features, the number of columns of your psi matrix do you need to determine this. And for both of these questions we have answers in the forms of HAL and ACE. So first I'm going to talk a bit about ACE. I think many people have heard this before, but what we try and do is we try and fit the atomic energy of an atom, which sums up to the total energy, as a function of neighboring atoms in a spherical cutoff. And we define the difference. We basically is a collection of relative bond vectors around the central atom, where we respect the element indices as well. What we then do is we use the single bond basis functions, which we evaluate on these bonds and separate the radial and angular components. And by summing over these basis evaluations on these bonds, we perform a density projection and explicitly incorporate permutation invariance into our model. Next, what we do is we perform a tensor product of these density projections and form this bold A basis. And what you can see if you sort of peek into this bold A basis, you can see many body correlations start to occur from the cross product emerging from the tensor product, which means that you have these basis functions of 1, 5 from one density projection into another, which sort of you see many body correlation functions occur, which explicitly incorporates body ordered functions in your ACE basis. Next, we incorporate rotation invariance by summing over all rotations, which we can reduce to a simple linear operation. But the whole idea is that we construct an atomic cluster expansion basis, which is linear in its coefficients, which explicitly incorporates the body orderedness of the ACE potential. Because it's a linear model, as I was saying previously, we can do linear regression. And today we're going to do Bayesian linear regression by taking the full Bayesian approach to this regular linear regression problem. And the idea is that your choice of prior actually sets the way you're going to regularize your system. So we can use Bayesian ridge regression, which is a very sort of a standard way of doing sort of regular least squares linear regression. But we can also do ARD, which will induce sparsity in our fit. And what we can do with that, we can start turning off and on basis functions in our ACE basis, and we'll see a little bit in that later. Next, we can set up a posterior. So if we try and fit our function, the idea is to try and fit for C, but by performing Bayesian linear regression, we don't just get one C, but we get a whole distribution of C vectors. So we can actually sample many different models fitting our data with sort of equal accuracy. And another key thing about Bayesian linear regression is that it gives rise to uncertainty. So anyone who's seen some Gaussian processes will most likely have seen these uncertainties emerging on any sort of prediction. And the computational cost of evaluating these uncertainties scale is order m squared, where m is the number of features in your basis, which means that this vector matrix vector product actually becomes quite expensive for very large bases. And what we're going to do today is sort of circumvent that by sampling coefficients from the posterior over coefficient space, this distribution over our solutions, and actually approximate the same uncertainty using a committee. So here we have our mean or maximum likelihood estimate, or the solution of our fit here in orange, and then we have sampled a whole bunch of different models from the posterior from which we can approximate this uncertainty. And the key thing here is that this actually introduces negligible extra costs of evaluation of the uncertainty, because we have to evaluate the basis once, which we can store in memory, and then the dot product of the C vector into the basis actually is computationally quite cheap, which means that your uncertainties you kind of get for free. And this is the key thing for hyperactive learning. So what we're going to try and do here is do active learning, try and build our basis based on some uncertainty tolerance and try and find new configurations and build a database. But the way we do this is we actually have our cheap error measure we've just discussed, and we're going to subtract it from the original potential energy surface, which induces some effective biasing potential towards uncertainty. So as you're going to run dynamics, what you're going to look for is configurations with high uncertainty or effectively low data. And what this does is it will generate configurations in regions where you don't have any data. And of course, once you're at a point where when you start to leave the training data, you should actually make sure that you don't extrapolate too far and generate unphysical configurations. And the way to do that is what we've chosen to do is you monitor relative force uncertainty. And the reason why we look at relative force uncertainty is that often actually modelers care about relative force uncertainty. So if you're trying to fit a liquid or phonon spectrum, the magnitude of the errors are actually vastly different, and the magnitude of the forces too. But actually, if you want to have accurate results, you're looking at a relative force error of on the order of a few percent, perhaps 3 to 10%. So this is why we chose to monitor relative force uncertainty to decide whether to stop the hyperactive learning, evaluate the ground truth DFT, refit the potential, and then generate a new configuration. And then the first question is, well, does this actually work? So here is polyethylene glycol from the 2 monomer units. You can see it up here. And we're benchmarking here hyperactive learning against active learning. So with tau equals 0, essentially you have no biasing. And then we start to increase the bias more and more. And as you can see here, these are the minimum number of stable steps out of 100 runs. So what you can see is that by the end, all active learning and hyperactive learning models, except for the bottom one, have managed to reach 100 million stable in these steps. So these are stable models. When you bias too hard, what happens is that you start to generate very unphysical configurations because you leave the potential energy surface too much, essentially, and you get garbage in, garbage out. You're starting to fit sort of very strange configurations with high energies and high forces you're not very interested in. But so what we're seeing here is that we still need the same number of data points. However, if you look at the cumulative number of exploratory steps we use to generate these configurations, we have to perform an order of magnitude fewer steps to build a database, which means you can really accelerate the way you generate these databases from scratch. Next, we're going to look at a slightly longer polyethylene glycol molecule. And what we did here is, as you can see on the left, we have some, we fitted on some 500K train and test data, and everything here is nicely on the diagonal, which means that the DFT and ACE energies very well agreed. So you looked at your test and train split and everything looked great, but then we started to turn on HAL, and it was finding these configurations very far away from the diagonal, which had huge errors on them. And the problem is that these energies actually are very low energy, or at least energies that should be accessible at 500K, and therefore will form during any molecular dynamics simulation at this temperature. It means that we actually should include them. And more interestingly, I think, is that if you look at these configurations, you can see they can exhibit some hydrogen bonding internally, which is low energy, obviously, and will form. And these are rare events, effectively, that you'll have to try and find using this hyperactive learning, and hyperactive learning biases you towards it, in turn helping you find these configurations. Then here on the right, we show that if you add some other high temperature data, that doesn't really help. And really the only way to get low errors on these configurations is to actually add them to your training database, and therefore you should use HAL to build your training database. Next, what we can do is add more and more data for longer and longer packed molecules here as isolated molecules, and use this ACE HAL DFT framework to build a database from scratch for increasing size of isolated molecules. And actually, with the final model, it turns out that we can run a much longer PEG molecule from the 200 monomer units in periodic boundary condition here in LAMPS, and actually determine the density with pretty good accuracy relative to experiments. So I think this is quite a nice example of going quite far with these models, because the model has never seen a periodic boundary condition nor even the size of this molecule before, but still we managed to capture the density without actually having seen a periodic image before. All right, so then we're going to switch gears a little bit and talk about alloys. And this is actually what I've been mainly focused on during the PhD. And my PhD has been around modeling phase transitions, especially in particular the melting temperature for alloys. And again, we can use the same HAL framework to build a database in a similar fashion. And here on the right, you can see this for a solid random alloy. So what we do is we run dynamics at, say, some temperature below the melting temperature, 800K. And we bias towards uncertainty, but not just we do MD steps, we also do Monte Carlo steps on the cell and do swap steps. So we adjust the cell vectors a little bit, and we do swaps, and we do accept and reject on this new HAL potential energy surface. And in the bottom bottom plot, you can see the uncertainty. So in iteration 6, pretty rapidly the uncertainty blows up. You reevaluate the DFT, add the training database, and then by iteration 16 and iteration 38, you see that the maximum relative uncertainty remains low, and it seems that you've collected enough data. You do the same for liquid. You increase the temperature a little bit, and now we can start to come back to this original question we were saying before, like how much data do you need? Well, we just collected 88 total configurations, 32 atoms each, and there's 1 total energy, 3 forces per atom, three times the number of atoms forces and 6 stresses, which means that there's 9,064 observations we've included into our database here. Next, we are going to fit the data using our ACE model, and the ACE basis we've chosen here is body order 3 and polynomial degree 12. And actually, if you look here at the top, or if you look at this plot here, this is our C vector. So you can see that ACE is quite interpretable, because actually, if you look at the coefficients in your solution, you can actually translate them to a basis function, and we can actually look at what the indices were and the elements, and you can actually see that the fit here. What we used is feature selection to try and determine which features have most relevance using ARD. And you can see here that by increasing the threshold, we add more and more basis functions, and the training error actually goes down, similar as for the test set error. So we're actually really nicely capturing the potential energy surface with more and more accurate resolution. Performance actually goes up a little bit, but these are still microseconds per atom per core. And I mean, just for illustration, when I started my PhD, our timings were similar, but they were microseconds per atom per core. So there's been about 3 orders of magnitude in one PhD, which is surely a lot. One key thing I think is very interesting here is that if you look at sort of this is a log plot, you can see some very big relevant coefficients on particularly these pair interactions. And what this is saying, I think, is that pair interactions or dimers essentially within your model are very relevant and actually contain lots of the binding energy and are very, very key to describing the potential energy surface accurately, which I think is quite interesting. Now we also actually have an answer to the number of feature dimensions or basis functions we needed for our design matrix, and it turns out to be 723 here by the number of coefficients we've used to fit. And so what we can do is these same models with increasing accuracy, we can actually look at something like the melting temperature. So we use nested sampling here to model this phase transition. Don't really have time to go into how that works, but as you can see, that the model got more and more accurate, and we actually converged very well onto the phase diagram and the liquid to solid phase transition as well using nested sampling. And again, putting everything together, we used 9,064 observations times 723 basis functions, which means actually that your design matrix is not very big, right? And actually, using ARD, you can do the actual regression task on your iPhone in about 25 seconds. So we're actually managing to really assemble sort of optimal design matrices and make efficient, fast fits on using very little computational power, and you can even do it on your iPhone. Now we're going to do a few more alloys I've done through the PhD. Here we added some magnesium to this aluminium silicon 10, and we first just put some magnesium in and kind of got some configurations which didn't really look very physical, but then adding it in the database, running another run of nested sampling, generating more data, we actually managed to converge again to the experimental melting temperature. And you can see actually during the solidification that you have these clusters forming inside this AL FCC lattice. And this is actually a precipitate forming in an effect called age hardening, right? So every car wheel you see on the street is made of this alloy, and the reason why it doesn't bend is because of these clusters impeding dislocations inside the alloy. So we're actually doing effectively metallurgy here using nested sampling. Another widely used alloy is titanium, aluminum, vanadium. What we did here is we did, again, same idea with how we run some liquid, bias towards uncertainty, look at relative and force uncertainty, and generate data. And we have some data for liquid, similar for BCC and HCP. And actually, running nested sampling, we see this liquid to solid, as well as this other solid to solid phase transition. And what we can do is we can look at the powder diffraction patterns, and you can, I think, clearly see there's a solid to solid phase transition here by comparing the BCC and HCP X-ray diffraction peaks, and confirming we're seeing, yeah, both a liquid to solid and a solid to solid phase transition. Another result here is molybdenum, niobium, tantalum, tungsten, which is actually also quite interesting because it's got excellent mechanical properties at room temperature because of two disordered transitions happening at around 900 K and much below the room temperature. And actually what's happening is that the niobium and the tungsten disorder, which sort of give it ductility at 300 K, and the molybdenum and the tantalum are ordered, giving it strength. And you can look at first short range order parameters, which sort of indicate whether there's repulsion or attraction between different atoms in the BCC lattice, either segregating or actually really attracting atoms inside the BCC lattice. And we can model this, and we can see this here in the left at the top. So I think that's about it. Just to sum things up, what we're doing in our group is really try and go from the configuration, run the DFT. Currently we use HAL and ACE to really create models quite quickly, and then of course go all the way and actually look at experimental, or try and find experimental, have results that agree with experiment. And we use the atomic cloud expansion, which is fast, accurate, robust. We use hyperactive learning to bias against uncertainty, and we are starting to really model physical phenomena as we've seen today, with densities of polymers, melting, hardening, chemical ordering, and also solid phase transitions.